Our next elastic constant is your modulus of rigidity, that is G. So the modulus of rigidity is, then we can know that as per Hooke's law, the shear stress is directly proportional to shear strain. We already see that in the Young's modulus, the normal stress is directly proportional to the longitudinal strain. So in case of shear stress, the shear stress is directly proportional to shear strain, and this is also up to proportional limit. Up to proportional limit. Right. So we can say that the one thing, that if I remove this proportionality sign, we will get the shear stress is equal to your shear strain into your modulus of rigidity, that is G. In some of the books, the G will be written as C, but we will use the symbol G for this course, and G is the modulus of rigidity. So the modulus of rigidity will be equal to your shear stress upon shear strain, and this is valid under pure shear stress. This you have to remember. This is the assumption of using G is equal to shear stress upon shear strain, and that is valid under pure shear stress up to proportional limit. That too up to proportional limit, this relation is valid. So we can say that for a given shear stress, if I make this shear stress as a constant, so we can write that the modulus of rigidity is inversely proportional to shear strain, or you can write shear strain is inversely proportional to the modulus of rigidity. So same we can say that if the modulus of rigidity of any material is more, this implies your shear strain is less, which implies shear strain is equal to the shear angle, that is the angle between the two mutually perpendicular planes after distortion, or the change of angle after distortion, that is phi. So if I increase this G, this gamma will decrease, hence this phi will decrease, so there is less distortion. Right, there is less distortion and the chances of failure will be less. So this is the meaning of your modulus of rigidity G. As in the case of your normal stress and normal strain, or you can say Young's modulus of elasticity, we already see that the slope of normal stress versus longitudinal strain will give us the Young's modulus of rigidity. In the similar pattern, we can say that the slope of shear strain and shear stress and shear strain graph, slope of shear stress and shear strain graph will give us your modulus of rigidity. It will give us the modulus of rigidity. So this is the definition of the modulus of rigidity, that is G. And just remember, this formula G is equal to tau upon gamma is only valid under pure shear stress. This is the assumption of using it. The third type of your elastic constant is the bulk modulus. The bulk modulus is used to determine volumetric strain under hydrostatic stress condition. Just please focus here. The bulk modulus is used to determine the volumetric strain under hydrostatic stress condition. Hydrostatic stress condition. What do we mean by hydrostatic? The hydrostatic stress condition means the direction and magnitude of all the normal stress acting on all the three mutually perpendicular planes are same. Right? Hydrostatic stress condition means the normal stress on all the three faces, that is X phase, Y phase and Z phase, on all the three faces, the direction and magnitude of normal stress, that is sigma, will be same if that is the stress condition, that stress condition is known as hydrostatic state of stress. Hydrostatic state of stress. And we will see also in your fluid mechanics that what is the meaning of hydrostatic. If there is a water at rest, right, water is at rest or any fluid is at rest, so at any point inside that water, the pressure in the all direction will be same. So that condition is known as hydrostatic state of stress, where the direction of all the three normal stresses on all the three mutually perpendicular faces are same and magnitude is also same. So I can write, if this is the case, then the normal stress on X face will be equal to normal stress on Y face, that is equal to normal stress on Z face, and that is equal to sigma. All these three are equal and that is equal to sigma. This is the meaning of hydrostatic state of stress. So we can say that as per Hooke's law, as per your Hooke's law, up to proportional limit, this is important, Hooke's law is valid only up to proportional limit. So I can say up to proportional limit, your hydrostatic stress is directly proportional to volumetric strain. Is directly proportional to volumetric strain. So I can write, if I remove the proportionality sign, so hydrostatic stress is sigma is equal to your bulk modulus K into volumetric strain epsilon V. This is volumetric strain. So from here you can write that bulk modulus is equal to sigma upon volumetric strain. Sigma upon volumetric strain, and the volumetric strain will be equal to, this is sigma upon, volumetric strain is change of volume into original volume. Change of volume into original volume. So the hydrostatic stress condition will be, if you replace the sigma with pressure, so I can write K will be equal to pressure into volume upon change of volume. Pressure into volume upon change of volume, right? So if I can say, if I applied a pressure, that is a stress, if I applied a load on a body or a pressure on a body, suppose this is some material, if I apply a hydrostatic force or pressure on this body, the volume of this body will decrease. The volume of this body will decrease because of this pressure, and if the volume is decreasing, then delta V is minus, right? Delta change is minus. So if this change is minus, then K will be minus. But we know that the value of elastic constant is always positive, so that's why I am using a minus sign here, right, to make K as a positive, because on the effect of pressure the volume of the body will decrease. If the volume of the body will decrease, this delta V will be minus. So to make K positive, I am using minus sign there. So this is the definition of your bulk modulus of elastic constant, and this is valid only under hydrostatic state of stress. Only under hydrostatic state of stress, right? So we can say that for a given load or for a given sigma, we can say for a given sigma, we can say that if this is the case, then volumetric strain is inversely proportional to the bulk modulus. Volumetric strain is inversely proportional to bulk modulus, or we can say that if you are increasing the bulk modulus, if I increase the bulk modulus, that means volumetric strain will decrease. That means change in volume will decrease. Change in volume will decrease. And we know what is the maximum value of K. We already see the maximum and upper and lower limit of the elastic constants. If you recall that table, we will see that the maximum value of K is infinity. The maximum value of K is infinity, that mu is equal to 0.5. If K is infinity, if I put the K value infinity in this case, if this is infinity, 1 upon infinity, that means the volumetric strain will be 0. If the volumetric strain will be 0, that means the change of volume will be 0, and if the change of volume will be 0, that means the volume will remain constant. Volume will remain constant. So if in that case, when you applied a pressure, but the K value of that material is infinity and the change of volume is 0, that material is known as incompressible material. Incompressible material means that material is not able to compress. We cannot change the volume of that body. That body is possible when the mu is equal to 0.5. In that case, change of volume will be 0. That material is known as incompressible material, and the example of incompressible material is your rubber, wax, clay and paraffin, and other material also which are having mu is equal to 0.5. What is the meaning of incompressible material? That the volume will be 0, the change of volume will be 0, but it doesn't mean that the change of dimension is also 0. Change of dimensions will be there, right? We can change, the dimensions are changing, but the change is like that, the total volume will remain same. We cannot change the volume. The total volume will remain same, but the dimensions in all the three planes are changing, because this hydrostatic state of stress is a normal stress, and because of a normal stress, your dimensions are changing. And if dimensions are changing but that volume will remain constant, that material is known as the incompressible material. Incompressible material. So this is the meaning of your bulk modulus, which gives us the volumetric strain in case of a hydrostatic state of stress. This formula is only valid for hydrostatic state of stress. We are saying that we have some conclusion from the hydrostatic state of stress conditions. We have some conclusions. These conclusions we will study these conclusions once again in your Mohr circle. When I discuss the Mohr circle in your combined stresses and strain, we are going to see all these things, but just to give you a brief that how we can define a hydrostatic state of stress. In hydrostatic state of stress condition, if suppose we can say this is a body, this black color body is under hydrostatic state of stress, that means in all the three directions, let us suppose I am taking this as x-axis, this as y-axis, this as z-axis. So in all the axes, the normal stress will be equal of magnitude and of direction, that sigma, sigma and sigma. Sigma x, sigma y and sigma z all are equal of magnitude and direction. This is your hydrostatic state of stress, and we will study that in this case there is no shear stress on any plane of that body, on any oblique plane. If this is a body, if this is under a hydrostatic state of stress, that is on this plane also sigma, on this plane also sigma, and all this plane also sigma, then if you take any point on this body and you can take any oblique plane, we already see in case of, just remember, we already see in case of your your shear stress, when a body is subjected to transverse shear load, we are saying what we see, that there is no normal strain on the cross section, but on any oblique plane there must be a normal strain, right? And in case of pure axial loading also, we can say that in case of a pure axial loading, or when a body is subjected to axial tensile load, there is no shear load on the cross section, but there is a shear load on a oblique plane. But in case of pure shear, or in case of your hydrostatic state of stress, there is no shear stress at all on any point on any oblique plane. No shear stress will be there, right? If there is no shear stress, then every plane is a principal plane. Every plane is a principal plane. We will discuss in our Mohr circle what do we mean by a principal plane. Just remember that principal planes are those planes where only normal stress is acting. Only normal stress is acting. There is no shear stress. On principal plane, there is no shear stress, only normal stress is acting. So, in case of the hydrostatic stress condition, at a point in all the oblique plane, there is no shear stress. That means all the planes are principal plane. And if there is no shear stress, there is no distortion. We cannot distort the body. And because we see that because of the shear stress, there is some distortion. If there is no shear stress, there is no distortion. If there is no distortion, then the shape will remain unchanged. Shape of that body will not change. And the last conclusion is the Mohr circle is a point on x-axis. We will define this in your Mohr circle. Just remember, the Mohr circle in case of a hydrostatic state of stress is a point on x-axis. So these are the conclusion of your hydrostatic stress condition. So this is a hydrostatic stress in which your body, your volume is changing, but because of this the body will not distort, right? Body will not distort like this. Body's volume is changing, length is changing, dimensions are changing, but there is no distortion. So if you want in any body no distortion, then the condition should be hydrostatic. In this case only we have pure normal stress planes, that is only normal stress is there. There should not be any shear stress, there should not be any distortion. So this is the meaning of hydrostatic stress condition.